few words about the lung volumes and lung capacities. So let's draw the lung first. That's a schematic lung. So this is your tidal volume, the volume that you breathe in and out during normal respiratory process. The volume that you can inhale on top of your tidal volume is inspiratory reserve volume. The volume that you can exhale after your normal tidal expiration is expiratory reserve volume. And the volume of air that stays in the lungs all the time is residual volume. Now, those are volumes in the lung. Now, capacities are the amounts of air that you can move. They reflect certain volumes that, like, for instance, okay, too much talking. For instance, this is a total lung capacity. That's basically a total volume of your lung. Now, this is vital capacity. So vital capacity reflects the sum of inspiratory reserve volume, tidal volume, expiratory reserve volume. That is the amount of air that you can move in or out. So say when you inhale to the top of your lungs and then you exhale as much as you can, that technically that exhalation volume should be vital capacity. Now this part, this tidal volume, inspiratory reserve volume, inspiratory capacity. And finally, this is called functional residual capacity. So if you suddenly stop breathing for some reason at the bottom of your exhalation, this is the amount of air that your lungs hold after you normally exhale. Next item on our agenda is the concept of dead space. So here you have two lungs. Primary bronchi, trachea. So essentially, the volume of air that's available for the gas exchange is this one. Volume that is contained inside of your respiratory zone. But your conducting zone of the respiratory system, your trachea, your pharynx, all the bronchi, it's not like a primary bronchi, so basically trachea and bronchi, they do not participate in the exchange of air, in the exchange of oxygen or CO2, but they still have to be filled with this air. So this is called anatomical dead space. And it is constant for a person. The volume of air that fills the trachea and the bronchi is permanent, right? But what also can happen, some of your alveoli can get damaged and can become dysfunctional. So in this case, let's say this part of the lung isn't functional. The rest is fine, but this is not. So this will be alveolar dead space. So the total dead space is this plus this. And when you consider the amount of air that you can use, that oxygen can come from, you have to take into account that the volume that you inhale will be distributed between the respiratory zone, and that's going to participate in the gas exchange, and the dead space, and that is not going to participate in the gas exchange. After that productive discussion of the volumes, the dead space, we can figure out the concept of minute ventilation and alveolar ventilation rate. So what is minute ventilation? It's your breathing rate multiplied by the tidal volume. Amount of air that's taken to your lungs over a minute. So breathing rate, let's say 12 breaths per minute, tidal volume 500 milliliters, minute ventilation will be 6,000 milliliter per minute. Okay, now, what is alveolar ventilation rate? In alveolar ventilation rate, we take, so alveolar ventilation rate. We take tidal volume, subtract the dead space, both anatomical and physiological dead space, and multiply it by breathing rate. So now you can see that is alveolar ventilation rate is an actual amount of air that gets into the alveoli. The question, what's better? To breathe faster but don't take too deep of a breath, or vice versa? We can do a kind of a math exercise. So let's say we have dead space at 100, let's say 100 milliliters. And tidal volume is going to be different. So normal, regular, we're going to put at, I don't know, 400, whatever. For a fast and shallow breathing, we're going to put tidal volume at 300, and for deep breathing, we're going to put it at 500. Okay, so the breathing rate, we're going to put 12, we're going to put 18, actually, you know what, we're going to put 16, and we're going to put 8. Okay, so in this case, interestingly enough, 8 is too low. You can't breathe really this slow. Let's say it's going to be 10. Yeah. So you take less but deeper. So difference is 400. Tidal volume minus dead space is 400. Multiplied by 10, 4,000 milliliters. Now here's the difference, 300 minus 100, 200 mils. With each breath go into alveoli, 16, 3,200. And with this one it's going to be 3,600. So you can see that if we breathe faster but reduce the volume that we inhale, that actually reduces alveolar ventilation rate. Okay? So again, the difference is the amount of air that gets into the alveoli with each breath, and that's breathing rate, and we multiply this number by the breathing rate to get alveolar ventilation rate. Obstructive versus restrictive diseases. So this is lungs just in general, and that's the conducting zone. So what's going to happen in obstructive diseases? For some reason, the passage for the air out or in will become narrower. which means it's harder to inhale, harder to exhale. That would be something like bronchitis, constriction of bronchi in case of allergy, things like that. Accumulation of mucus in the respiratory passages. So what's going to change? If you think of it, you can maintain only certain number of breaths every minute. So what you end up with is your tidal volume will probably decrease because you can't inhale as much. What's going to increase is your functional residual capacity, FRC, okay, which is expiratory reserve volume and residual volume. So your FRC will go up. So, residual volume will go up. More air will remain in the lung all the time. Okay, so those are two things. Those are few things that are characteristic of the obstructive disease. Also, you can measure the flow rate. Okay, you can measure how much air you exhale, how fast you exhale the air. Obviously, if the road will narrow down, there will be traffic jam, and your respiratory flow will decrease. In the restrictive disease, such as pulmonary fibrosis, what happens is that's your healthy lung, and that is your diseased lung. The actual volume of the lung goes down. So total lung capacity goes down, vital capacity goes down. But your breathing rate will stay pretty much normal. Okay.